The visitor was supposed to follow the rules. Pause. Gravity is a law, not a suggestion. But as Oumuamua turned its back on our sun, it did something that defied every calculation in our books. It pushed. Pause. No fire, no gas, no debris. Just a silent, surgical acceleration into the dark. Pause. We called it a rock because we were afraid to call it a machine. But today, the shadow of the architect becomes too long to ignore. Science is a fortress built on the bedrock of the known. It is a system designed to categorize the chaos of the universe into neat, predictable boxes. But when Oumuamua entered our world, it didn't just rattle the gates of that fortress, it brought the walls down. As the object began its long retreat from our sun, the data coming from our deep space arrays started to whisper a story that no one was prepared to hear. The first anomaly was the geometry. To understand why Oumuamua's shape is so troubling, we must look at how we measure things in the dark. We cannot see the object directly as a photograph. It is too small and too far away. Instead, we watch the light. We watch how it flickers as the object tumbles through the void. This is called a light curve, a rhythmic pulse of brightness and dimness. Oumuamua's light curve was like nothing we had ever recorded in the history of astronomy. It changed in brightness by a factor of 10 every 7 to 8 hours. For the mathematicians, this was a smoking gun. To produce such an extreme variation, the object had to be incredibly elongated. It had to be at least 10 times longer than it was wide. Imagine a needle, or perhaps a thin, flat disk, 400 meters in length, tumbling chaotically like a splinter in a storm. In our own solar system, among the millions of asteroids and comets we have mapped, we have never seen anything with these proportions. Most natural objects are rounded by gravity or jagged like broken glass, but they maintain a certain balance. Oumuamua was an extreme outlier, a statistical impossibility. It looked less like a product of a collapsing star system and more like a piece of deliberate engineering, a shape designed to minimize the impact of interstellar dust while traveling at 87,000 kilometers per hour. But the shape was merely the prologue to the real mystery. The true defiance of the laws of nature came when Oumuamua passed its closest point to the Sun. In the realm of orbital mechanics, gravity is king. Everything follows a path carved by the mass of the Sun. We knew Oumuamua's mass, we knew its velocity, and we knew exactly where it should be every second of its journey. But then, the numbers stopped adding up. As the object began to move away, it didn't slow down as the Sun's gravity demanded. It gained speed. It received a small, persistent, non-gravitational kick. In any other case, a scientist would say it is a comet. When a comet gets close to a star, the heat vaporizes the ice beneath the surface. This creates jets of gas, natural rocket engines that push the object forward. But Oumuamua was silent. It was clean. It was dead. We turned the Spitzer Space Telescope toward it, an instrument capable of detecting the tiniest traces of heat and gas. It watched Oumuamua for 30 hours. It found nothing.
No carbono monóxido, no carbono dioxide, no daste, no water vapor.
The object was not outgassing. There were no jets. There was no fire. The mysteries we explore here are deep, and they require a watchful eye. If you find value in this journey through the unknown, subscribe to the Event Weaver. Help us keep the light of inquiry burning in the dark. Now, let us return to the anomaly. The scientific community was paralyzed. If there is no fuel being burned, and there is no gas being expelled, how can an object accelerate? It is like watching a car speed up on a highway while the engine is turned off and the fuel tank is empty. This is where the intellectual tension reached its breaking point. The traditionalists began to propose increasingly desperate theories. They spoke of hydrogen icebergs, chunks of frozen hydrogen that would be invisible to our telescopes. But hydrogen ice is so fragile that it would have evaporated millions of years before reaching our system. They spoke of nitrogen fragments from a distant, shattered Pluto. But the sheer volume of such fragments required to explain Oumuamua would mean the galaxy is a crowded graveyard of broken worlds. A conclusion that contradicts everything we know about star formation. And then, a different voice emerged from the most prestigious office in the world of astronomy. Professor A.V.A. Loeb, the chair of the Harvard Astronomy Department, looked at the same data and reached a conclusion that his colleagues were too afraid to voice. He didn't look for a natural explanation that didn't fit. He looked for a technological one that did. He realized that if the acceleration was not coming from the object itself, it had to be coming from the light. The pressure of sunlight, the tiny, almost imperceptible push of photons hitting a surface. For this to work, Oumuamua would have to be incredibly thin, less than a millimeter thick, and incredibly light. It would have to be a sail, a light sail, a piece of interstellar technology designed to harness the power of stars to cross the vast gulfs between worlds. The math worked. The physics was sound. The only thing that was missing was our willingness to believe. The academic world is not always a sanctuary of pure reason. Often, it is a battlefield of egos and established dogmas. When Professor A.V.A. Loeb published his paper suggesting that Oumuamua could be an artificial thin film, a light sail, he wasn't just presenting a hypothesis. He was throwing a torch into a library of old books. The backlash was immediate, and it was fierce. Critics called the idea sensationalist. They argued that extraordinary claims require extraordinary evidence. But Loeb's counterargument was simple and devastating. Where is your evidence for the natural explanation? To explain Oumuamua as a natural object, we have to invent things that we have never seen. We have to imagine a hydrogen iceberg, a chunk of frozen gas that exists nowhere else in our observations. We have to calculate the survival of such an object through millions of years of exposure to starlight. And when the math shows it would vanish, we have to invent even more complex reasons why it survived. Loeb argued that we were being cosmically arrogant, assuming that nature must always have a boring explanation, even when the data screams otherwise. Think about the sheer scale of the engineering required for a light sail. If Oumuamua is indeed a sail, it represents a level of technology that makes our own rockets look like steam engines. To harness the pressure of photons, the material would need to be incredibly reflective, perhaps a composite of carbon fibers or a metallic film unknown to our metallurgy. It would be a mirror the size of a city block, but weighing no more than a few kilograms. As it tumbled, the light would hit different parts of its surface, creating that tiny, persistent push we observed. It wouldn't need an engine. It wouldn't need fuel. Its fuel is the universe itself, the constant, eternal rain of light from the stars. But why was it tumbling? A functioning probe usually maintains a stable orientation. Oumuamua was spinning chaotically. Every 7.3 hours it completed a full, jagged rotation. This led some researchers to a more haunting conclusion. Perhaps Oumuamua was not a functioning scout, but a derelict, a piece of space junk, a broken wing from an ancient, interstellar vessel that had been drifting through the void for billions of years. Imagine the tragedy of it. We spent decades looking for a signal from a living civilization, only to be visited by the graveyard of one that is long gone. A silent, reddish shard of technology, carrying the dust of 1,000 different star systems on its skin, passing through our home like a ghost ship in the night. The Breakthrough Listen project, funded by Yuri Milner and backed by the greatest minds in physics, decided to take the gamble. They pointed the massive Green Bank telescope toward the object. They listened across a wide range of frequencies, from 1 to 12 gigahertz. They were looking for a heartbeat, a digital ping, a leak from an onboard computer. The world held its breath. For a few days, we allowed ourselves to dream that the silence was about to end. But the results were as cold as the void itself. Nothing. No radio signals. No narrowband transmissions. Oumuamua was as quiet as a tomb. Does the silence prove it was a rock? Not necessarily. If you found a smartphone from 21st century Earth in a forest a million years from now, and the battery was dead, would you conclude it was just a strangely shaped stone? Of course not. You would look at its internal structure, its materials, its design. But we didn't have that luxury. We couldn't land on Oumuamua. We couldn't touch it. We could only watch its shadow vanish. The more we looked at the numbers, the more the natural explanations began to feel like desperate fairy tales. If it was a dust bunny, a loose collection of frozen particles, the sun's gravity would have torn it apart the moment it got close. If it was a nitrogen iceberg, we would need to explain why Oumuamua was the first interstellar object we ever saw, because nitrogen worlds are incredibly rare. Statistical probability was on Loeb's side. If Oumuamua is a natural occurrence, then there must be quadrillions of such objects in every cubic light year. The galaxy would be so crowded with these needles that we should be seeing them every week. But we don't. We saw one. One unique, impossible, silent intruder. The idea of a light sail is not science fiction. It is an engineering reality that we ourselves have already begun to test. In 2019, the Planetary Society launched LightSail 2, a tiny spacecraft that successfully raised its orbit using nothing but the pressure of sunlight. We know the physics work. We know that photons, though they have no mass, carry momentum. When they hit a reflective surface, they transfer that momentum, providing a constant, gentle push that can, over time, accelerate an object to incredible speeds. But the scale of Oumuamua is what haunts the imagination. To achieve the non-gravitational kick that our telescopes recorded, this object would need to be extremely thin and possess a surface area vastly disproportionate to its mass. If we follow the calculations of the Harvard-Smithsonian Center for Astrophysics, we are looking at a structure that is less than 1 millimeter thick. Imagine a massive, shimmering membrane, dark and reddish from eons of exposure to cosmic rays, stretching across the void like the wing of a fallen bird. It is a design that nature simply cannot replicate. No collision in an asteroid belt, no volcanic eruption on a frozen moon, and no gravitational tidal force can create a sheet of material that thin and that durable. This realization brings us to a terrifying crossroads in our understanding of the galaxy. If Oumuamua is a sail, then the great silence we have lived in for so long is a choice, not a necessity. It means that the void is not empty, but filled with the artifacts of civilizations that have reached a level of mastery over light and matter that we can barely conceive. Some researchers suggested that Oumuamua was part of a larger network, an automated scout sent ahead of a fleet or a discarded piece of a much larger mission that passed through our system 10,000 years ago. We must remember that in the vast scales of cosmic time, human civilization is a mere blink of an eye. Oumuamua could have been traveling for 100 million years before it reached us. It might have been launched by a civilization that has already vanished from the universe, leaving behind only its machines to wander the dark forever. The frustration of the scientific community was palpable as the object began to fade. We were like detectives arriving at a crime scene only to find that the evidence has already been incinerated. This led to the birth of Project Lyra, a theoretical mission designed to do the impossible: catch Oumuamua. The mathematics of such a mission are staggering. Oumuamua is leaving us at a speed of about 26 kilometers per second. No current rocket in our inventory can catch it in a straight chase. To reach it, we would need to use a complex gravitational dance, swinging a probe around Jupiter and then dive-bombing the Sun in a maneuver called an Oumuamua maneuver, using the Sun's gravity as a slingshot to propel a craft to extreme velocities. We would need to launch a probe within years, not decades. We would need to develop laser thermal propulsion or nuclear electric engines that currently only exist on our drawing boards. The debate over Project Lyra revealed the true state of humanity. We are a species confined to a single room, watching a miracle pass by our window, unable to even open the door and run after it. Even if we could catch it, what would we find? Would we see a smooth, metallic surface engraved with the symbols of a foreign star system? Or would we find a jagged, ancient ruin, its senses long dead, its purpose forgotten? The silence of Oumuamua is its most powerful weapon. It forces us to fill the void with our own fears and our own hopes. Professor Loeb remains steadfast in his conviction that the burden of proof has shifted. He argues that we should no longer ask for extraordinary evidence to prove an object is artificial. Instead, we should ask why we are so desperate to believe that everything in the universe must be a cold, dead rock. The discovery of Oumuamua has ended the era of cosmic isolation. Whether we like it or not, the evidence of something else, something intentional, has crossed our path. As we look at the maps of the stars, we no longer see points of light. We see potential origins. We see the vast, dark highway that Oumuamua is now traveling. It is heading toward the constellation Pegasus, returning to the eternal night from which it came. It leaves us behind on our small, blue island, changed. We are a little less certain, a little more humble, and a lot more watchful. The detective story of Part 2 ends not with a solution, but with a transition. We have analyzed the shape, we have measured the speed, and we have debated the origin. Now, we must ask what happens next, because Oumuamua was not the last. In the years since its departure, we have already seen others. The cosmic traffic is picking up, and the next visitor might not be so silent. The story of Oumuamua is not just a chapter in an astronomy textbook. It is a mirror reflecting our own limitations as a species. We are like ancient mariners who saw a steamship on the horizon and tried to explain it away as a strangely shaped whale, because the alternative was too overwhelming to contemplate. As the object recedes into the constellation Pegasus, we are left to grapple with the debris of our own theories. One of the most profound realizations to emerge from this encounter is the concept of interstellar archaeology, a term popularized by Professor Loeb. He argues that we should no longer focus solely on radio signals, which are fleeting and require both civilizations to exist at the exact same moment in time. Instead, we should look for bottles in the cosmic ocean, physical artifacts discarded technology, and derelict probes that can survive for millions or even billions of years in the deep freeze of space. Oumuamua was our first such bottle, and we almost missed it. It reminds us that the galaxy might be a vast museum of dead civilizations, a place where the machines of the past outnumber the living minds of the present. If Oumuamua is a piece of space junk, it tells us that interstellar travel is common. It tells us that someone, somewhere, mastered the art of sailing on light long before our ancestors even discovered fire. The skepticism of the scientific establishment is a natural defense mechanism. It is a way to protect the Goldilocks version of our universe, where everything is natural, predictable, and dead. But Oumuamua has permanently cracked that shield. Even the researchers who reject the alien hypothesis are forced to admit that this object is a statistical unicorn. Whether it is an exotic hydrogen iceberg or a light sail, it represents something that our current models cannot fully explain. This intellectual tension has sparked a new era of vigilance. Programs like the Galileo project are now being designed to search specifically for these interstellar objects, or ISOs. We are building the Vera Rubin Observatory in Chile, which will be able to scan the entire sky every few nights with unprecedented depth. We are no longer waiting for the aliens to land on the White House lawn. We are looking for their shadows in the data. We must also consider the silence of Oumuamua in a different light. If it was a scout, why didn't it try to communicate? Perhaps we are looking at it from a human-centric perspective. To an intelligence that can span the stars, a planet in its early technological stage might be no more interesting than an anthill by the side of a highway. They might have sent billions of these probes across the galaxy, automated, indifferent, and silent. They are not looking for us. They are simply mapping the terrain. As we reach the conclusion of this scientific detective story, we are left with more questions than answers. Why was it reddish? Why was it tumbling? Why did it speed up without a tail? The data we have is frozen in time, a limited set of observations of a ghost that has already left the building. We will never see Oumuamua again. It is now a resident of the deep dark, moving toward the stars at 26 kilometers per second, a silent voyager carrying its secrets into the infinite. But Oumuamua has given us a gift, the gift of curiosity. It has reminded us that the universe is far stranger than we dare to imagine. It has forced us to look up from our screens and our local conflicts and realize that we are part of a much larger, much older drama. The anomalies of the Voyager are not just anomalies in a spreadsheet. They are invitations. An invitation to build better telescopes, to launch faster probes, and to expand the boundaries of what we consider possible. The shadow of the architect remains long and mysterious. We may never know who built the sail, or what world produced the needle. But we know they were there. We know that the void is not empty. And as we move into the final part of our journey, we will look at what Oumuamua left behind, the legacy of a silent guest, and the future of a humanity that is finally, truly, looking at the stars.